with 3D inkjet printing systems, engineers can fabricate hybrid structures that have soft and rigid components, like robotic grippers that are strong enough to grasp heavy objects but soft enough to interact safely with humans. These multi-material 3D printing systems utilize thousands of nozzles to deposit tiny droplets of resin, which are smoothed with a scraper or roller and cured with UV light. But the smoothing process could squeeze or smear resins that cure slowly, limiting the types of materials that can be used. Researchers from MIT, the MIT spin-out Inkbit, and ETH Zurich have developed a new 3D inkjet printing system that works with a much wider range of materials. Their printer utilizes computer vision to automatically scan the 3D printing surface and adjust the amount of resin each nozzle deposits in real time to ensure no areas have too much or too little material. Since it does not require mechanical parts to smooth the resin, this contactless system works with materials that cure more slowly than the acrylates, which are traditionally used in 3D printing. Some slower curing material chemistries can offer improved performance over acrylates, such as greater elasticity, durability, or longevity. In addition, the automatic system makes adjustments without stopping or slowing the printing process, making this production-grade printer about 660 times faster than a comparable 3D inkjet printing system. The researchers used this printer to create complex robotic devices that combine soft and rigid materials. For example, they made a completely 3D printed robotic gripper shaped like a human hand and controlled by a set of reinforced yet flexible tendons. The researchers says that their key insight was to develop a machine vision system and completely active feedback loop. This is almost like endowing a printer with a set of eyes and a brain, where the eyes observe what is being printed and then the brain of the machine directs it as to what should be printed next. The research appears in the journal Nature. This paper builds off a low-cost multi-material 3D printer known as Multifab that the researchers introduced in the year 2015. By utilizing thousands of nozzles to deposit tiny droplets of resin that are UV cured, Multifab enabled high-resolution 3D printing with up to 10 materials at once. With this new project, the researchers sought a contactless process that would expand the range of materials they could use to fabricate more complex devices. They developed a technique known as vision-controlled jetting, which utilizes 4 high frame rate cameras and 2 lasers that rapidly and continuously scan the print surface. The cameras capture images as thousands of nozzles deposit tiny droplets of resin. The computer vision system converts the image into a high-resolution depth map, a computation that takes less than a second to perform. It compares the depth map to the CAD computer-aided design model of the part being fabricated and adjusts the amount of resin being deposited to keep the object on target with the final structure. The automated system can make adjustments to any individual nozzle. Since the printer has 16,000 nozzles, the system can control fine details of the device being fabricated. The level of control afforded by the system enables it to print very precisely with wax, which is used as a support material to create cavities or intricate networks of channels inside an object. The wax is printed below the structure as the device is fabricated. After it is complete, the object is heated so the wax melts and drains out, leaving open channels throughout the object. Because it can automatically and rapidly adjust the amount of material being deposited by each of the nozzles in real time, the system doesn't need to drag a mechanical part across the print surface to keep it level. This enables the printer to use materials that cure more gradually and would be smeared by a scraper. The researchers used the system to print with thiol-based materials, which are slower curing than the traditional acrylic materials used in 3D printing. However, thiol-based materials are more elastic and don't break as easily as acrylates. They also tend to be more stable over a wider range of temperatures and don't degrade as quickly when exposed to sunlight. The researchers used thiol-based materials and wax to fabricate several complex devices that would otherwise be nearly impossible to make with existing 3D printing systems. For one, they produced a functional tendon-driven robotic hand that has 19 independently actuatable tendons, soft hinges with sensor pads, and rigid load-bearing bones. They also produced a six-legged walking robot that can sense objects and grasp them, which was possible due to the system's ability to create airtight interfaces of soft and rigid materials, as well as complex channels inside the structure. The team also showcased the technology through a heart-like pump with integrated ventricles and artificial heart valves, as well as metamaterials that can be programmed to have nonlinear material properties. The researchers are now looking at using the system to print with hydrogels, which are used in tissue engineering applications, as well as silicon materials, epoxies, and special types of durable polymers. They also want to explore new application areas such as printing customizable medical devices, semiconductor polishing pads, and even more complex robots.